there and rally people to come down.
Today's speaker is Bryan Grenfell. Now, Bryan is not all that easy to figure out on the web. He's one of those really discreet person. We happen to know that he was born in the 50s. I was born myself in the 20th century. And he is a British population biologist. British, you know. Actually, it's Welsh. Basically, it's Welsh, okay? And that's the specific type of nuclear body, okay? Like the Welsh. All right. So Bryan started his career at Imperial College London. He got his degree there, a PhD from the University of York. And then he spent time in Cambridge. Oh, you've got the right order, excuse me. York, Sheffield, Cambridge, and Penn State before Princeton. His interest, I think, can be described in 2 words: disease ecology. In general, that covers a lot of things. He has a number of prizes. He is a member of the European Academy of Arts and Sciences, the Huxley Medal from the Imperial College, the Scientific Medal of the Zoological Society of London, and he's also, of course, a FRS, a Fellow of the Royal Society. But there is another initial that took me some time to figure out. He's also an OBE. That turns out to be an officer of the most excellent order of the British Empire. Like, you know, that really impressed me. And so, yeah, this man is a most excellent order. Bryan, it's going to be hard to follow this.
Thanks, Francois. As ever, the wonderful Belgian sense of humour. And of course, there's no British Empire anymore, so anyone who wants to leave at this point. Okay, so I'm going to cover a lot of ground. I know it's a somewhat general audience. I'm going to stick with the light side just to start with, but I'll give you a shout out when we're done. I'm going to cover a lot of ground. Please do ask any burning questions. I'll take brilliant questions. So I want to talk about nonlinear dynamics, really. I'm a predator-prey dynamics guy originally, and I love nonlinear dynamics. And I want to talk about how we characterize dynamics, characterize predictability and its limits in epidemics. Epidemics is very important in an applied sense, so we need to think about the impact also of control. And I'm going to touch on the problem of cross-scale dynamics, and I'll explain what I mean about that in a minute. And I think that's a fundamental problem for all of us in this room. So I want to talk about the simplest case, which is acute immunizing infections, like measles, as we'll see. I'll explain what those are. I want to talk about the relative impact of intrinsic nonlinear dynamics and external drivers like climatic and other drivers. Ecological question, really. I'm going to talk about complexities like partial immunity and evolution. And then I want to talk about dynamics across scale from the molecular biophysical level up to the population and global level. And there are a ton of collaborators here, and I'll highlight quite a few people in the group in a minute, and internationally, and in particular, a very strong interdigitation with just mentioned. So here's the stuff I love. Here's the nonlinear dynamics of measles. This is measles in England and Wales. Vaccination started about then. But a fundamental question in science really is we all have to cut the dynamics off at some scale. We can't explain everything in terms of quantum theory at different scales, so we have to work out where we can cut the dynamics off. This looks as though there are nice patterns, but there are clearly a ton of complexities bubbling away underneath this. First, there's these are human populations that are transmitting the infection, so there's network dynamics. There's individual variation between individuals, in particular this idea of super spreaders, which I'll come to later on. And there are very intricate, from biophysical, really genetic, immunological dynamics within that. So how can we then have the temerity to move to, if the dynamics here and the complexity ramified right up through scales, we'd be in trouble. But can we cut the dynamics off and understand these dynamics in isolation just to start with? Well, we can if we make two seemingly grotesque assumptions. So measles, you're born and after maternal immunity, you're susceptible, you've not seen the infection before, you then acquire the infection from an infectious person, and then you're immune for life. And as we'll see, that's a reasonable assumption for something like measles. So if we make just that simple assumption, it's a couple of 100-year-old assumption. The history of mathematics in epidemiology is very old. And we need to make another assumption, which is going to offend a lot of people, I suspect. At some scales it isn't going to work, but let's assume that we have reasonably mass action mixing. Just work with me for a minute on that. And then a more subtle assumption, and we increasingly have to relax this, is that there isn't a feedback between the size of the epidemic and people's behaviour in trying to avoid it. So I'm going to assume that in these historical epidemics didn't happen. And just those assumptions.
I have another one. Jesse, I have another one. Jesse. I have another one. Jesse.
This leads to, just to show the equations, this leads to the well-known susceptible, infected, recovered SIR model. We can write all that down as simple differential equations. Births feed into the susceptibles. Vaccination reduces births so little if you move people into the recovered class immediately. And then the key thing is there's this nonlinear term. The infected times the susceptibles, that comes from the mass action assumption, and that's kind of a classical predator-prey term, and a nonlinearity in terms of the nonlinear dynamics. And there's a key twist to this in that beta, the transmission rate per contact, isn't necessarily constant. Okay, fantastic. Isn't necessarily constant, and therefore this is really a pendulum for those who can look quickly at the mathematics. This makes it a forced pendulum, so it might have interesting dynamics. So just as a cartoon, a lot of people know this, but just for a bit of background, the key kind of talismanic number here is the reproduction ratio of infection. If everybody's susceptible, what's the number of secondary cases that Lars, who's checking his email, would if everyone around him, if Rob and everyone around him was susceptible, and I'm assuming 5 because it's easy to draw the stuff. So therefore you would get an exponential increase. But then quite quickly, if we assume this is on a fast time scale, so birth for matter, you will deplete the susceptibles very quickly, and therefore the effective value of R, which starts at 5 there, will drop very quickly, the actual number of secondary cases. So at the peak, each case causes 1 case because the others are already immune if you're making 5 contacts. And that then eventually the epidemic will turn over. This is a result of the non-linearity. It's really kind of the epidemic clockwork, if you like. It's called herd immunity, and that threshold of susceptibles is where you're trying to get in terms of vaccination. You don't need to vaccinate everybody to get rid of the infection, because susceptibles who are still around are protected indirectly by vaccination. So it's the effect of the non-linearity, but it's very important in terms of control. So that's the essential first component of the dynamics. And I want to talk about measles. It's very transmissible, as we'll see presently. It's historically it was a big killer, and is still a big killer in many countries, in sub-Saharan Africa in particular. It's very significantly immunosuppressive, and I'll characterize that in a lot more detail later on. Seemingly, and this is a whole lecture really, there's lifelong immunity following infection. Evolution is not important here. There was a very effective live attenuated vaccine developed in the 60s, but despite that, there's still a significant burden of disease, measles in Disneyland and so on, as well as a major burden in developing countries. And there are rich historical data sets. I apologize that some people in the room have seen this movie more than some people have seen Gone with the Wind, but nonetheless. These are data, not a model. Very, very rich data sets recording. This is London in yellow and the rest of the country in white, recording these lovely oscillatory dynamics. Irregular up into the 40s, and into the 40s, and I'll explain why in a minute, these annual epidemics. And then there were lovely biennial epidemics after that. Everything pretty synchronized, but if you kind of stare at it in the troughs here, then the epidemic seems to move away from the big places to the small places. And we'll come back to the significance of that later on, but very rich data sets. So we've got our model, we've got our data sets, we can make much more complex models, but there's a bunch of mathematics that shows that simple models should be okay for us here, and I can go through that for those who are interested. We can use a ton of model fitting procedures to get at the dynamics, some parts of the dynamics, and then predict other pieces so that we can try and test the models and so on. And we use, there's a bunch of methods, but we use state space models, which allow for the dynamics and the measurement process, and that lets us get at these dynamics. And we particularly like natural experiments. We like changes in birth rate or changes in vaccination, as we'll see, which act as natural experiments, and that gives us more power. If you can predict a change in cyclicity in general, it's much more powerful. So here's an example. We fit a state space model to the short term, 2 weeks ahead dynamics of the infection, essentially estimating the seasonality of transmission, which I'll come to in a minute. And then we run it forward, this for London, through the pre-vaccination era, and we see this beautiful bifurcation into biennial cycles from annual cycles, and that was because of the baby boom. The baby boom, the gas coming into this little engine was going faster in the baby boom, and therefore you've got annual epidemics, and that winds out into biennial epidemics, but it's quite subtle because of the seasonality of forcing. Here's a picture of the seasonality of forcing. Here's one of those biennial cycles. And this was, I'll come to climatic drivers and disease quite a bit later on, but this was really primarily kids crowding in schools. So these notches that the postal system is used to send the stuff in, so there are slight lags. These notches reflect summer holidays, the Easter holiday in the UK, and Christmas holidays and so on. There's a great measurement error I made at one point. A little bit later on, there's a very exciting looking spike. It was actually a postal strike. So there's an accumulation of cases. So that there's a kind of linear filter on top, which is the measurement process. So the dynamics in the simple model would wind down. It's being pushed periodically, so like pushing a swing, so you get these recurrent cycles. Best understood post-natural enemy dynamics in ecology, I think. So here's some lovely work by Otto. It's hard to predict very, very accurately actually into the vaccination era, because amazingly they weren't sure exactly where they distributed the vaccines spatially. Here's just a crude fit to the pre-vaccination data, and though it's much noisier in the vaccination era because it's just not as resonant and there's a whole bunch of work on that, you still capture the overall patterns predicting out of sample through this quite a long period. So you can do quite well in terms of these kind of post-fictions of long-term dynamics from the short term. So there are complexities with prediction. First complexity is stochasticity. This is a discrete state space, and therefore it's discrete numbers of individuals. You can't make a continuum assumption. In enormous populations, there are never any zeros in the troughs between epidemics. But below, though, in the UK and the US in those days, about 250,000, 300,000, you get increasingly chains of transmission, break in epidemics, and therefore need to be recolonized from larger cities. And this is this idea of the critical community size. And Quentin Cadron in the group has done very nice work showing there's still signatures of predictability in those, even in these very, very small and irregular populations, but that's another story. This is a ton of work which I'm not going to focus on much, on spatial-temporal dynamics underlying those sorts of movies I showed. So-called gravity models used a lot in social science and borrowed a lot by the epidemic community recently. One I like a lot, a refinement of this is by Max Lau in the group. a new competing risks framework, and this is a picture of using competing risks, which is the most compared to the kind of background or external driving of these big cities, which is the most influential city in terms of restarting the measles in the pre-vaccination era, and this is the second most. And you see Liverpool and Manchester come out as the most, and Newcastle regionally, but London is kind of depressingly important for us regionalists. It's extremely important. And then local dynamics come out a little bit more if you look at the second most influential. Max has then taken this right through into the vaccination era, and a very cool thing is, as things get more stochastic, this is just a crude picture, but the map is dominated by London early on, and then the black area here is external forcing, or forcing we can't attribute. And by this point, when it was very low, it's known genetically from the virus that was really international forcing. And this is really where we'd like to get. Unfortunately, we're not there, as I'll describe in a minute, with measles in developed countries. If we're going to eradicate it, which I think eventually we should try to, we need to get to this point where the meta population is kind of really subcritical. But there's a lot more work to be done there. So the other complexity is just the intrinsic dynamics. So I showed you the baby boom, and you saw there were annual epidemics, common sense, right? If you just take a model and you crank up the birth rate to much higher, so in Niger the birth rate is 3 times as high as it was in those historical data from the UK and the US, then common sense, you should get these very regular dynamics. So this was work a few years ago by Matt Ferrari, so you look at Niamey, the capital of Niger, actually great data, and you get nothing like that. So the model predicts annual cycles, the data are not annual cycles at all, so the model's wrong, okay, and the data are a kind of valid measure of what's going on. And if you fit those state-based models, here's the seasonal swing of transmission in the UK. In the UK compared to Niamey here, and there's much more of a swing of transmission, and that's probably a lot of work recently by Anita Barty, actually, now at Stanford, shows that this is probably seasonal people movements, actually, people moving in the dry season into the edge of cities, away from agriculture, away from the fields into the edges of the cities. And so you get these very irregular dynamics. And if you take a weakly damped pendulum like that and you force it hard enough, then you can get chaotic dynamics. And that's what we really see. It's consistent with, at least with chaotic dynamics. So if you run the model for a long time, you get this bifurcation diagram. So here's the strength of seasonality. If there's low seasonality, you get biennial or annual dynamics, which is like London. And then if you crank up the seasonality, you get these chaotic dynamics with actually deep troughs and lots of fade-outs between infections. So northern Nigeria, the big cities there, are probably very important for keeping measles going in Niger, even though it's a 20 million population. The critical community size here is probably well over 1 million. So very different dynamics, but characterizable in terms of these seasonal swings. And Jess Metcalf and her group and collaborators are very interested in using cell phone data and other things to get at much more mechanistically how these seasonal swings in infection are driven by people movement. You also get great unpredictability right up to the edge of elimination, and again, working out smart vaccination strategies to get at that is a kind of a very important way. So that was in Niger, where things are very different, but even subtle differences in seasonal forcing can make a difference. And this was Ben Diel, who was a great postdoc in the group until recently, and this is comparing the US and the UK. And in the US, the UK data tended to be annual or biennial patterns, as I showed. The US are much more exotic, 4-year cycles, 3-year cycles at roughly similar periods, and slightly before that, and 3-year cycles for the folks interested in nonlinear dynamics are peculiar, right? Period 3 implies chaos, something interesting might be happening. And then fitted, again, these state-space models, and you can explain the irregularities just in terms of the seasonal pattern of transmission, it's much higher variance in the US. There's a much longer trough, and that's because the summer holidays are about 3 to 4 weeks longer in the US, and even that subtle difference can drive you quite close to chaotic dynamics. So in big cities in the UK, you would tend to get biennial dynamics, just a bifurcation diagram, and one could work out the Lyapunov exponents and then negative in this case, just by fitting the model and getting this from the Jacobian. But you're much closer to the line's a bit fake. You're much closer at least to the edge of chaos or chaotic dynamics. This isn't really low chaos because it's a discrete, spatially extended system, but you certainly get deterministic reasons why you get divergence from limit cycles. So quite subtle differences in the forcing can lead to quite large differences in the dynamics. So the third complication is incredibly important, and now I'm relaxing my behavior change doesn't matter assumption. A classic example here was, thank goodness, Ebola. The models there predicted you get an exponential doubling time of the epidemic. It turned over much sooner than susceptible depletion would tell us. The CDC, there's a lot of, this is another story, had a very pessimistic model where you might get 1 million cases, turned over much before that, and that was because of changes in hospitals being brought in, but also considerable behaviour change. We've not worked specifically on that, but we do work with wonderful colleagues at the CDC, the US measles folks, and this is an outbreak, this isn't measles in Disneyland. I would love to write a paper entitled Measles in Disneyland, a Mickey Mouse model actually. That would be fantastic. But this is an outbreak in counties in Ohio amongst the Amish population who didn't vaccinate that much. And the story here, it's a bit faint, but the effective reproduction ratio was about 10 at the start, so the epidemic should have just shot through the counties. They managed to get vaccination going, but really not enough, though they did a great job. And this was because of behaviour change. Young adults brought it in, who were from the Philippines, where there was a huge outbreak, and they agreed to self-isolate and stay at home. Nobody died in this outbreak, fortunately, so that behaviour change helped control the initial parts of the epidemic. Of course, there are, in my view, bad versions of behaviour change, which is vaccine hesitancy, and so it's a kind of double-edged sword. But in prediction terms, this makes things much tougher, because this is the stuff of social science, right? It's much, much harder, much more formidable problems to work out. So, thinking about cross-scale dynamics, then we know schools are important, right? So can we quantify that? Well, we have those beautiful spatio-temporal series for cities and towns. We don't have parallel data, I wish we did, at the school level, so we can't get that at it explicitly. But there are some data sets, and this is wonderful recent work by grad students Alex Becker and Ruthie Briger, and we found actually in the Wellcome Library in the UK had digitized all the medical officer of health records back into the 1800s, and there was a wonderful, if you're into this kind of thing, outbreak of measles in Woolwich, in the London borough, in 1904, with lots of wonderful school-level data. So they fitted these epidemics, and here are two examples. It's a slightly technically tough thing to fit these very stochastic epidemics. At the back here are replicates of the stochastic fits. But you get R0s at the school or at the age class level very high, which is not unexpected. We expect that. Extremely high. And here's an example of a high one, Elizabeth Street School, and a lower one. But the range is, the median level is extremely high. Now, do we really think that works? Well, here's just an example of what measles can do. I just reanalyzed a famous historical epidemic in Greenland, and a young man who was a sailor, came in from Denmark to Greenland, went to a dance party and infected 204 people. Right, so fomites, respiratory, absolutely spectacular. So the effective reproduction, R0 was 204, because no one had this in living memory. And then everyone else was infected in the next generation. There were two other little towns. They tried to quarantine. Nobody died, fortunately, but everybody got it. Right? right? So those 50 numbers are not crazy. So that's worrying for the modern era. So this is a map dug out by Alex and Ruthie. So here are vaccination levels in some California schools, and you know, if you take R0 of 12 even and you multiply that by 1 minus this, then that's a lot bigger than 1. If R effect is bigger than 2, it will infect everyone in a small context, if you think about the doubling process. So this is kind of an exploded measles bomb, if you like. It could happen. It's interesting it's not happened yet. And that's probably because the US actually does really well in terms of mass vaccination. There's probably a huge blanket of immune people amongst which these kids and their parents are residing. So maybe it just can't percolate yet. And Ruthie and Alex are making network models to try and connect the schools, and then we can think about, from our CDC friends, trying to get more intricate data. But it's a problem. There was a big outbreak where I come from in Swansea a couple of years ago, and the schools were heavily involved, and the effective reproduction ratio was 5 or 6 there. So, you know, it's potentially a serious problem. So in conclusion, epidemic predictability, there's only one big source of nonlinearity, that's my take on it, in the absence of behavior change, and that's the clockwork thing. So it's a forced pendulum. So compared to the weather forecasting folks who do a fantastic job, I think it's there'll be experts in the room, but it's a much easier problem than epidemic systems. Now, predictability is important for outbreaks, but I think it's more important in a sense for refining our understanding of things. And it's not that we can predict, because if it's chaotic we can't, or if it's very stochastic, but we can understand the limits of predictability, which is, I think, the key thing. And it's this strong herd immunity and modest seasonality often led to these stable limit cycles, but you can get more complexities. So can prediction work in systems with imperfect immunity? So this is wonderful work, just to show a more complex system. This is wonderful work mainly by Ginny Pitzer, who was an EEB alum and was a postdoc here now at Yale. And rotavirus, very serious, the major at the time in the world, still is probably gastrointestinal viral infection, maybe 500,000 deaths in the pre-vaccination era. Vaccines were being developed, so the CDC again were very interested in working out what was going to happen. It's very imperfectly immunizing. There's strange structure. It's much, much more complicated. There are several different types of the virus. Immunity only lasts about a year. So Ginny made a model. You can actually parameterize all this amazingly from vaccine cohort studies. I won't go through the details there, but you can read the paper. And essentially, you're an infant, you get primary infection, you're very sick then, you're probably 6 months of age. You then can get the infection again and again. The first time, you have explosive diarrhea and vomiting. And R0 here was 30, probably 30 or 40, hugely transmissible. Vaccination mimics the primary infection, so it reduces that. Possibly reduces that transmission. So the question is, was there herd immunity? Well, you remember that if the infection responds to birth rates, that's a sign that there's a nonlinear constraint on things and that there's herd immunity. So I didn't think this was going to work at all, but Ginny thought, well, let's just look at the birth rates in the US pre-vaccination and see what we get. And first of all, here's the mean week of rotavirus activity, and it's winter infection. Some states didn't report, but in the West, earlier on in the series, then the epidemics came first, and then later on, very interestingly, this was a great mystery that had never been understood, it all equaled out rather. And Ginny saw that the birth rate patterns were exactly like this. They used to be much higher in the West, in California, and then in this period, they kind of reduced and became much more uniform. And if you crudely just look at the date of the peak against the birth rate, then at high birth rates it's kind of earlier on. So Ginny took this model and completely independently then, pretty much independently of fitting anything to the vaccination data, predicted what would happen, assuming that vaccination is a bit like a reduction in birth rate. Okay? So this is what we observed. This was the pre-vaccination envelope of the epidemic. And then the first year they didn't really get their act together, and then the epidemic was later and slower, and that's a sign of herd immunity. And the model, and this is pretty much out of sample, kind of qualitatively captures that pattern nicely. What it also does, in an applied sense, is it lets us get at the prevalence of infection here against vaccine coverage, and there's quite strong indirect protection. So even though you're not immune for long, if you can stop the primary infection and the explosive diarrhea and so on, you slow down transmission. So there is indirect protection. Ginny also predicted in this paper, at about this point, that the epidemic would go biennial, would go every other year, and indeed it did. So that's a genuine out of sample prediction. And we lucked out on the phase, actually. I mean, it could have been 180 degrees out of phase, but we were lucky with the phase. So conclusion for rotavirus, complicated, but again, strong signals of nonlinearity, very important. Can we see nonlinearity in the series? No obvious culprit for environmental drivers in the US here. It looks as though really highly transmissible. It's that birth cohort thing that's dominating. But that's not in general true. There are very interesting, and again, this is something that Len Shevakova and Jess and folks associated with PEI are very interested in, is environmental drivers and climate change and infectious disease. And this is work mainly by Jeff Shaman, very beautiful work, looking at anomalies in absolute humidity, and this does much better than Google flu trends, upon which don't let me get started. There's a dip in absolute humidity before the kickoff of the flu season in general. And the nice thing here was that Jeff did this by reinterpreting guinea pig experiments. So you have laboratory experiments looking at temperature and humidity. Absolute humidity was the driver, and that captured this. But there's a ton more to do to understand global flu, and in particular the long-term interplay with the nonlinear dynamics, and I'll come back to that in a second. There's a ton more examples. I'm not going to go through them. One from our group, and again, this was Jess and I collaborated with Ginny Pitzer again on this, who led this work. There's a lovely story with respiratory syncytial virus, which is a very important lower respiratory infection, for which there's no vaccine yet. And the lovely thing is, it's got herd immunity, but it's also got strong seasonal drivers. It really likes dry winters, essentially, dry, cold winters. And in states, in Florida, you get very regular annual epidemics. You get biennial epidemics in states with dry, cold winters, so that the meteorological conditions, I mean, we can't pin this down yet because there's no guinea pig experiment equivalent, but meteorological conditions are tuning the nonlinear dynamic periodicity. And there's like a ton of examples from vector-transmitted infections where I think there's huge potential for getting together high-class weather and climate stuff with infectious disease dynamics. But you always have to drill down to the individual level, I think, and into the molecular biology. Big challenge for long-term flu prediction is rapid pathogen evolution. It's a big challenge for a lot of these existential threats. So both measles and flu, just in brief, are RNA viruses. They both have quite a high error rate in the polymerase, but measles is it doesn't change in any kind of, if you look at the evolutionary tree through time going in this direction of the surface molecules, it really doesn't change in any strong way. A lot of people here will know, even apart from occasional pandemics, which is a much bigger jump, you get this beautiful ladder-like phylogeny. It's essentially a strain jumps enough to avoid immunity and then spreads around the world. So it's a beautifully structured pattern. So that means we really do care about the individual level dynamics, and we can't only think about averaging across individuals. So is there a signature of herd immunity in these evolutionary jumps? And again, you can look at the details of this in this paper by Axis and al. This is from Louis Stone's group. And we found here that for Tel Aviv, where you have particularly good, well-reported influenza-like illness data, you can capture and predict. Here's a test of the model, and this is when they did it. So this was out of sample after the pandemic. You can predict a few years ahead in terms of a nonlinear oscillator with kind of loss of immunity, and they had absolute humidity as a significant term in this model as well. But what you can't do is predict, you have to reset the system at these jumps, at these periodic jumps when the virus changes, the cluster jumps. There was one last year that the vaccine wasn't matched to very effectively, and they're quite considerably important. And this was the pandemic, which we were lucky was a very minor pandemic this time. So even in influenza, you can do this, though no other data sets really work as well as telemedicine, which is why this was a PNAS paper and not a science paper. Marta Luxa and Michael Lassie, who was visiting recently Marta's at the Institute, predicting seasonal flu, this is a hobby horse, is like one of the wonderful problems. Seasonal influenza is the model organism of cross-scale dynamics, right? You can go from the biophysics and the molecules up to the global level and back. And they're doing very important work here. My solution, knowing this was work with Nim Pathy, who was a postdoc, is predictions would be great, but actually we just need to make a cross-protective vaccine. That's really what we need, and the world needs a cross-protective flu vaccine. And it's really economic dynamics and market failure. It could be done, I think, now, but it isn't deployed. There's similar stories with Ebola. That's a very important, not population dynamic result, ecological result, but it's really economic dynamics. So I want to finish by drilling down to the molecular level, to the within host level. There are many cases like influenza where you need to do this, and to understand antimicrobial resistance, we're going to need to do it to understand influenza evolution. I'm going to talk about the population implications of immunosuppression of measles. I said measles was very immunosuppressive, and this was work by Mike Minner, who was a postdoc visitor from Emory, absolutely fantastic scientist. And what Mike found when he plotted measles cases, these are annualized measles cases where we can get, in the countries we can get intricate enough data to do what I'm going to describe, against all-cause mortality against other infectious diseases, there's a kind of positive relationship, and this has been pointed out before. But you see, it's not a simple one. Here's the start of vaccination, and there was a drop a little bit earlier. We can't quite see what's going on there, so it's not simple. And there's a whole industry led by Peter Abbey, who's a Danish clinician. There might be some non-specific effect of the vaccine, though it doesn't seem that it's totally correlated with vaccination here. So that does work with some vaccines, controversial, that it's some kind of adjuvant of the immune system. Mike's assumption was that it was a direct effect of measles immunosuppression. And this was because we looked at a paper by some colleagues who became involved in this, led by Rick de Swart, and this is going down to the individual level, you take a macaque model for the infection, and you use the GFP-labeled virus, and then you can do extraordinary imaging to get at exactly what cells are infected. And they're cells of the lymphoid system, and in fact they're the SLAM receptor, the CD150 receptor that the infection uses to get into cells. That's a signature of a central memory T cell. So it attacks memory cells, and these are the data that they got. You get a reduction in the total number of lymphocytes, and it's reconstituted, but it's reconstituted amazingly. They couldn't take it through much beyond this with these experiments, but have some data further on. It's reconstituted, it seems, with measles-specific immunity. So you get immunosuppression, but then the immune system really bounces back. But if you had immunity against other infections you'd picked up before and survived, measles gets, it seems, this is a hypothesis, gets rid of the memory against them. So how would you see if you can see that in the population data? Well, what you do is you take the age-specific cases of measles, and then you say, if I'm a 2-year-old, and let's say that immune amnesia lasted 2 years, then I'm putting a category of immune amnesia, and then that total category is regressed against the mortality to see whether that could account for those lags that I talked about. And you can vary the width of this kernel. And here's an example. This is for the UK data. Here's the next data set. So the curve here is the R squared of the fit. And you saw initially the slopes of the dynamics didn't really match up. But you see that the slope, let me run it again, if you don't assume any lag, any amnesia, then you get a slope between measles cases, which it really is then. But the pre and the post-vaccination data are very different. There's no kind of unified picture. But as you increase the lag, and you see that the kernel will increase to this level, then the fit gets better and better. And this is the match between that measure of amnesia and the mortality data. So as we go through that again, lots of moving parts in this picture, you can see that these curves move together to a unified picture pre and post vaccination, and you get kind of all we're doing is varying that kernel. You get a remarkable fit at the optimum. Just an ecological study, a remarkable fit matching roughly a 2-year lag in this immune amnesia with the effect on subsequent other infectious disease mortality. And at the optimal fit, I won't run it, this curve is after a kid is born and paternal immunity takes way. This is the relative risk that you get of subsequent infections, and that timing matches this 2-year thing very nicely. And here's the example from not quite such a good data set. Here's the example from the US. And again, the key thing is it works pre-vaccination as well as in the vaccine era, which is a kind of an ecological piece of evidence, it's no more than that this isn't a non-specific effect of the vaccine. The natural fluctuations of measles pre and pre-vaccination also, when integrated right, and with the same kernel as the UK fit, and post-vaccination here, explain these patterns reasonably well. So it occurred to me when I was making this talk, what this pre-vaccination thing is here, it's a delayed effect of the baby boom. That's what's happening, because births turn into cases. The pattern of births with a lag is what's causing those fluctuations in mortality pre-vaccination. So strong patterns, and I've got a ton of caveats here, and you can read Mike's paper to get at those. In high mortality countries, the data aren't as good, but also immediate deaths swamp the effect. So you only really see it in these relatively low mortality countries. But really the smoking gun here would be, and our colleagues are doing this, cohort studies in humans, sampling pre and post a measles epidemic. There was just one in Holland. And there would be long-term and very expensive macaque models where you could infect animals with another infection and then give half of them measles, and you can imagine the design. So this is absolutely not a smoking gun, but you see that by thinking about the within-host dynamics, you can get very interesting feel for what's happening at the population level. So overall then, summarizing the talk overall, there's some evidence for kind of emergent simplicity in epidemiological dynamics. We do need to see these simple patterns for something like measles. For influenza, you do need to think much more in the weeds and much more about the intricacies. But a lot of questions like influenza dynamics, antimicrobial resistance, disease and anthropogenic change, for example, where you need experiments at different scales, we really need to cross scales between ecological, behavioral, molecular level, as well as between natural and social sciences, I think. Because to understand why we have not deployed the no-brainer of a cross-predictive flu vaccine yet is a question from many other fields. There are very important bioethical questions about the testing of the Ebola vaccine. It's a kind of very interdisciplinary question. And to get at this, it's crucial to clarify human behavioral dynamics and again human movement and aggregation. And I know that's something that, again, Jess and her group and collaborators are very interested in. Just one final point that I'm particularly interested in here is in terms of the next steps in this immunological stuff is there's wonderfully interesting data from human genetics and molecular biology about the impact of acute viral infections and the interaction between immunity and the incidence of non-communicable diseases, asthma in children, type 1 diabetes. And I think we're very interested in a very preliminary way looking at the population dynamic aspects of that. And I think that's, again, going to be another very interesting frontier for cross-scale dynamics. Okay, thank you.
We have time for questions.
Can you come a bit closer?
I'm interested that you mentioned that you take into account the changing of the virus, like the mutation of the virus, to the dynamics. So I'm curious about when the virus changed, the susceptible population also changed because it's kind of a different virus. And also the vaccine also may change because the vaccine that may use for in the past virus may not use for them. So do you think we should change those two factors based on the change of the virus?
So it's a great question. So the first one, what we do in those models is very, very crudely, if the virus has jumped, you just change the susceptibles in the model at that point. So you very crudely capture it. There are then a ton of so-called phylodynamic models where you have the sequence data in and the immunology and try and do a lot more detail. In terms of the cross-protectiveness of the vaccine, yeah, I mean, I think there are candidates for cross-protective influenza vaccines that work even across subtypes of influenza now, for example, so that they would work right across H5N1 and the currently circulating things. You would probably always cocktail it, that virus, though, with the current seasonal virus, because you would not want to make a mistake there.
Other question?
So I was just wondering what the patterns in flu are like. It's like, you know, the seasonal pattern for the north is very clear. What does it look like in the tropics? Are there any data from Australia where the seasonal patterns of aggregation are different?
Yeah, so it's a great question. So the north, so the US, huge population, obviously, that disappears every summer. Roughly that in the south, though the Southeast Asia has huge populations. In the tropics, you tend to get much more persistence because it's much less seasonally driven. But the western tropics are not important because there's nobody there, and the eastern tropics are incredibly important. So the new patterns often come out of Southeast Asia, not so much out of real southern countries because there just aren't so many.
So I have a question for you. All viruses so far. So what happens with bacterial diseases? Same sort of pattern, or much more complicated because of
the most measles-like example is pertussis whooping cough.
Okay.
And it does show those changes in cyclicity and so on, but much tougher and a much more complicated beast. You know, so you see effects of herd immunity, but I think the pure form of those effects are these viral infections. But it's a great question. The bacterial infections are very important. I mean, some of the bacterial things, you know, meningitis and so on, are commensals anyway, you know, and disease is a much more complicated thing. You know, something like malaria is again extremely good at fighting the host immune system.
questions there.
This might be a dumb question, but with this kind of information, the more we learn about this kind of dynamics, would it be possible to start acting against the disease by public health approaches rather than only vaccination? We have the vaccination, but could we, by dealing with how schools are interacting, how we do self isolation, etc., how efficient would that be versus just pure vaccination?
It's a great question. So, well, of course, that is done for something like typhoid or cholera. Sanitation is kind of the most important thing in a lot of those contexts. I think it's a very important question because I think not so much as well as if you can make a good vaccine, you just vaccinate the heck out of the population and you try and achieve herd immunity if you can. If that's not possible, and there is not thinking of MERS and SARS, there's not a coronavirus vaccine at the moment. There's not that you can't make vaccines for quite a few things. Very important to try to. Then you really do have to do those isolation and quarantine and so on. And that was how Ebola was brought under control. So you probably have to do both, but a good, safe, licensed, mass-produced vaccines are really powerful.
Would you tell us more about your thoughts on building models as a way of testing the limits of predictability?
Well, I mean, what I meant by that was you can if it looks like a limit cycle, you're in good shape, right? Unless there's a change in behaviour. With those US data, and let alone Niamey, so Niamey is a good one. You knew it was going to start in October. It starts at the start of at the end of the rainy season, but you had no idea how big the epidemic is. If it's a strongly chaotic system, your ability to predict ahead it diverges very quickly. Your ability to predict ahead is very small. So I think fitting the model and then getting an idea of what the dynamics of the system are then kind of guides how you do that program.
So that's a good question for you, Brian. So unless I missed it, I didn't see the data on HIV. The model work for this particular infection?
So there's a ton of work on HIV and Ruthie Briger in our group does a lot of work on that. It's much slower, and if you just look at the math of that oscillator, if you have about the same R0 and a very long infectious period, you kind of lose the imaginary damping thing, so you end up with much more logistic-like dynamics. It's also there, partner change, network dynamics are much more important. These mass action assumptions are much more difficult.
One question.
Brian, I'm obviously interested in vector biology, so from my naive perspective on these issues, clearly that would add some dynamics to the situation. Can you comment on that, let's say for yellow fever, where it's still immunizing? Or?
So we can argue about this. I mean, if you can make a good, yellow fever, yellow fever. If you can make a vaccine, then you're not going to like this. You can treat it like maybe a directly transmitted infection. And I think IEDs might be different from anopheles. Day biters and night biters are different. So the detail will be in the biology. I mean, not the fact that we haven't got vaccines against dengue and chikungunya is a very serious problem for the world again, actually. And again, the climate change implications of that are quite important. But it's a great question. I think the details are what's on the vector, actually. I suspect people tend to, it's how's the infection moved around over long distances. And I think the day biters and the night biters are I think, different there.
Okay. Bring Brian again.